Hi, my name is Cabral and I'm showing to you a seminar about symbolic computation of dual metrics associated with Stackel-Killing tensors on qubit space. This work was performed with my collaborator, Basílio. We are from Brazil, from Tocantins state. And now, to begin, I will consider the problems of isometry. In isometry of a curved space, we can consider, for example, in order to simplify the problem, we consider the general coordinate transformation. As you can see, these are the usual equation for that. Okay, but the question is about the invariant form of the metric. Considering the equation number 2, the metric will be form invariant by the transformation from the unprimed to primed system, and this implies in the form presented in the equation number 3. Number 3 is the general isometric condition. Okay? Well, from the general isometric condition, we can consider a symmetry transformation, or better, an infinitesimal transformation in the form. Okay, the form considered uses a vector field. Okay, xi mu. Consider the transformation and using the structure of equation number 4, we have the components showing in this way, as you can see in the equation number C, and joining the first terms in epsilon, we get the equation number 7. From this equation, you can see that you have the famous Lie derivative of a metric with respect to a xi field. Okay, with components, we have this form. Well, from this form, it's possible to rewrite this equation using the covariant derivative from the metric Gemini. If the metric is non-degenerate, we can represent the isometry in the infinitesimal form by means of the famous equation called the Killing vector equation. Well, if the xi mi component of the vector xi, we have the condition for the xi to be a Killing vector. As you can see, there is the definition of the covariant derivative, and I'm using the Levi-Civita connection. Okay. Now, if it's possible to consider the generalization of the Killing equation for high rank. Okay. In this case, we have a definition of rank and Stackel-Killing tensor, a general form. In fact, this tensor is a completely symmetric tensor. It's a completely symmetric tensor by means of a completely symmetrized covariant derivative. It is equal to 0. Well, as application of the Killing tensor, we can consider the Hamiltonian of a particle with unit mass in a qubit space represented by a metric Gemini. In this formulation, as you can see in the equation number 12, we are using the inverse of metric, since we are considering the metric non-degenerate. Well, it's important in this problem to consider the evolution, the phase space of some function that depends from position and momentum. Okay. Well, if you consider a temporal evolution for some quantities in the phase space, for example, a contraction of a Killing tensor or Stackel-Killing tensor of rank 2 with the momentum, that showing that has a similar form of Hamiltonian. Well, this quantity that you can see in the equation 14, this quantity is some kind of object that you consider in the phase space. But for this object, it's possible to show that applying the Poisson bracket, this equation entails equal to 0. Well, from the same reasoning, we can construct a general conserved quantity by considering the contractions of the Stackel-Killing tensor with the momentum. For the rank 2, you have the usual equation. In this case, n equal to 2, and we follow these equations shown before. Well, it's important that in this case we can observe a duality behavior in the phase space evolution. The duality behavior it's possible to observe from the equation number 18. In this equation, we have, for example, a metric xi in a space with a Killing tensor j, or a metric j in a space with Killing tensor xi. This is a kind of duality because in this form of quantities involved, we always have 0 for this Poisson bracket. In this case, we have a dual metric contravariant component. Let us consider a special case of that. For you to understand this situation, it's important to consider some examples of metric. In this case, I consider the Kerr metric in a specified coordinates. You can see that from this metric we also obtain a Schwarzschild metric only by using a equals to 0 in all components. You can go from one to another metric using this limit. The problem is, what is the Killing tensor for this metric? Well, to obtain that you need to solve this equation. In fact, it's a system of partial differential equation. We have a lot of components, as you can see, and the solution for that, for example, a general solution, can depend from 4 coordinates. Okay. The solution, a special solution for that, as you can check by a symbolic maple, are the components of xi. For each component, I'm using the symbol tilde g, using a equal to 0 and u equal to cosine of theta. This is the general solution of that system of partial equation. Well, it's very known that the Kretschmann's scalar can be obtained by the full contraction of the Riemann tensor. This expression for the Schwarzschild metric will have a simple structure where you have a constant that involves mass, or m in this case. It's possible to notate that the structure presents a singularity, a unique singularity for r equal to 0. However, when you consider a dual space-time, you have a non-trivial structure. This non-trivial structure, as you can see in the Maple worksheet, assume we have a number of terms, a large number of terms. In order to reduce this number, we must choose a equal to 0, m equal to 1, and the following description. Even in this case, we have a non-trivial structure that's not related with the usual Schwarzschild-Kretschmann scalar. In order to see the details, let us consider the Maple worksheet in order to perform some calculations. Okay. In the Maple worksheet, we have all the metrics here. We have the metric here with all the terms. You can see 5 arbitrary constants here, but according to the choosing constant, we have very different results. That's a non-trivial result. For example, if you calculate the rich tensor components, you can see there is a lot of terms. You need to choose some constants. In the particular chosen constants, we have this expression. Even with a simplify, you cannot reduce the number of terms. Yes, you can see that that this expression has a non-trivial structure that's not possible to consider that is a coordinate transformation from the Schwarzschild metric. You can see from this structure of the Ricci tensor. Okay. The problem becomes more complicated if you consider the full contraction of the Riemann tensor, the Kretschmann scalar. As you can see, if you try to compute that, you see that thousands of terms, thousands of objects, as you can see. In order to see this component, you must choose some particular constant values. Yes, you can see this one. Well, this constant chosen here entails a large structure of the Kretschmann scalar. Well, considering this structure, you have in fact a large anisotropy since you have the term u. U term is in fact is a cosine of theta. Consider another chosen of constant. We have a smaller structure, but even in this case it's not possible to relate it to Schwarzschild. As you can see, in fact, we have a Schwarzschild metric, but a non-trivial structure in a dual metric. In order to detect this structure, it's possible to analyze the singularity structure. Well, for example, if you choose m equal to 0, for Schwarzschild metric, in fact you have a 0 scalar, but here is not 0. In fact, it entails a non-trivial scalar considering a lot of constants. With another choice of constant, avoiding all the structure with cosine of theta, considering also some terms, more terms involved. Yes. Now, simplifying this expression, we have usual scalar Kretschmann here from Schwarzschild, but only for this chosen constant you have this one. Now, as you can see, considering all the combinations, you have a plot of three cases: 1 equals to 0, 1 equal to 0.1, and the Schwarzschild matrix choose m equal 1. In fact, they have a singular structure equivalent, but only for r going to 0. But in fact, they are different structure graphically. To see a more detailed situation, consider, for example, in another choice of constant, we have another kind of singularity, a ring singularity. For example, in the case of m going to 0, as you can see in this plot. The structure of this plot you can see, for example, in a 3D plot. For the usual Schwarzschild metric, this is the plot of Kretschmann. You can see a smooth surface. However, if you consider another choice of constant, we have a non-trivial structure. Yes, another shows here. As you can see, they are not completely related, even with constant chosen. This is one situation, another one, and the trivial one. They are not continuously deformed from one to other. So in this case, you have a non-trivial structure. For example, you can return to the usual case to remember that if you choose this constant, we have the usual situation, that's the Schwarzschild, and in the Ricci tensor here, in fact, you have all components equal to 0. Okay. Now, if you try to consider the Kretschmann scalar with the same constant used above, in fact, you have the usual expression. Well, the non-trivial metric that's very important in this case that you can explore some kind of exotic space-times, and Maple with symbolic computation is very useful to detect this structure. For example, here, and another structure non-trivial here. In fact, it's a symbolic computation, and at the same time you have a picture of the non-trivial structure of the Kretschmann scalar, as you can see in this simple example. Thank you for attention.